Thank you very much, Professor, for that very nice introduction. Can you hear me okay? Is it all right with the acoustics and the recordings on, I believe? Yeah, simulation-driven design. I'm very happy to be here to talk about simulation-driven design. I could probably talk for 7 days, but it's just an hour, 45 to 50 minutes that we can dive into it, and then there will be a bit of time for Q&A. I basically want to show you how to utilize simulations to create better products. That's the idea. And I will have to, so to say, not go into many details. I want you to develop an understanding what is simulation-driven design and what is based on it. There's even a newer kit on the block. It's called data-driven engineering, and simulation-driven design is the basis for that. So I'll talk about this a little bit. So it's really an introduction, a few examples, and yeah, as said, I'll skip most of the details, if not all, so that you really can get away with a few things that you should bring home. The sweet spot for simulation-driven design in naval architecture and in other fields, as I will explain further down the road, is energy efficiency. Basically, what you can see here is a first example of simulation-driven design. It's a small vessel. If you look very closely, particularly at the bulb region, there are changes to the geometry that influences the wave field in this particular example. And when you look at the fuel, it's basically changing, going down up till something like 90-something%. So you change the geometry in order to make it a better geometry for the particular purpose that you have in mind. And a classic approach, that is typically called now simulation-based design, is that you would do this manually. You would basically change something, maybe based on intuition. Then someone says, okay, let's go for another simulation. You double check. You might have something that's a little better, and then you more or less iterate a few times. And in simulation-driven design, as I will show you shortly, we look into hundreds of design variants that you really want to pick from in the end. Okay, typical applications, they are not only in naval architecture. In naval architecture, there are hull forms, propellers, energy-saving devices, everything that is hydrodynamics, more or less. But increasingly also aerodynamics when you think of wave-assisted ship propulsion. And a few more examples from totally different fields. It's turbines, it's turbochargers, it's all sorts of pumps where you can directly apply simulation-driven design. So it's not a very specific field to naval architecture, but nicely in naval architecture, I think many of the principles that I'm talking about and many of the things that are used now in other fields were actually developed within naval architecture. I already introduced that other term, simulation-based design, which is a little older, and I just try to explain a bit more why we are actually going and bother about simulation-driven design. Often in a design task, you have multiple objectives. So it's not just a single thing that you want to improve, but you have to consider many things at the same time, and they are typically in competition. And what happens is if you have, say, at least 2 objectives, for the sake of illustration, that's easier than showing 5 objectives. Okay, with that manual iterative process, you maybe have a handful of designs that you can study, okay, because then time's up. And we distinguish feasible and infeasible designs. Infeasible designs are those where at least one constraint is not fulfilled. In naval architecture, it might be you have not the right displacement, or the clearance between your propeller tip and the hull is too little. These type of things are constraints. And then you pick more or less from those few that you have developed a better design for your particular purpose. And in simulation-driven design, the picture looks much more dense. You have a lot of variants to choose from. If you analyze dozens or even hundreds of variants, you can understand, okay, what is actually the cause and effect of certain things. And then you can choose a new design based on what is called Pareto optimal, meaning that you have among those different objectives, you have designs that cannot be improved with regard to one objective without actually making another objective worse. This is the definition of a Pareto frontier, very important concept. You know that from your own lives. You can not do lots of sports and still have the time to do lots of studying, and vice versa, and you cannot have lots of time with your friends and still be a lot of time in the lab. So you have to make a compromise. The ingredients for simulation-driven design are, in general, geometric modeling, then the simulation itself, or the simulations, doesn't have to be only one type of simulation, and then what is called exploration and exploitation. I'll briefly go into the various things shortly. The idea is that you crank through that process again and again, okay? You just don't want to do it once or twice or 3 times, as we have seen in the previous picture on the left, but you want to do it 100 times. And because that's getting boring after the 5th time or the 6th time you're doing this, let the computer do the hard work. This is an animation, another example. It's a fast monohull, as you can probably guess. I will have a similar example later on. And as you can see, the geometry is changing, and with the geometry, the flow field is changing. It's actually here computed with fine marine from Cadence, a viscous flow analysis, including the free surface. So that takes a little while, a few hours to compute. And if you have, so to say, a long weekend, then you can look into maybe a few dozens of variants. And I guess there are very few people here in this room, if anyone at all, that would readily say, this is the best one I can think of, and this is probably also from a hydrodynamics point of view the best one. Hydrodynamics, unfortunately, in a way, doesn't really always show easily. So it's very hard to say this hull is better than that hull, unless you have 50 years of model basing experience, and they don't come very often, those people. Okay. So, introduction. I hope you have an idea why we are doing this and what are the ingredients, and now we'll phase into how it's actually done. I'll start with optimization, because optimization is something that you do all the time. When you go from A to B, you already start optimizing because you think of how can I get there, maybe the cheapest or the fastest or the most convenient, whatever. We already have 3 objectives. And the constraint might be you have to be at an estimated time of arrival of, 11 o'clock, being here in the lecture hall, for instance. The idea of optimization is you typically have a black box. It's illustrated here in 2D because we in the optimization environment, we say we have 3 variables, things that we can change, okay? That you can control yourself. And often, in design, you have maybe 10 or 15 or 20 or 25 free variables, or even 50 free variables. And a 50-dimensional space is hard to figure, so we'll do it with 2 dimensions so that it's easier to understand. This is the design space, and no one knows where is the sweet spot, where is, so to say, the optimum to be found. Okay, so what we do is, basically in optimization, we just probe. We have our objective. It's a single objective problem here. So, and maybe a few constraints, and inequality constraints, for instance, meaning that everything that is in the red part of the picture would violate a constraint. So you can go there, but it would not be a feasible design, and everything that is, so to say, light blue would be okay. So what you do is you basically probe. Well, let's check here, or let's check there, or let's check there. And if we want to maximize something, we sort of say probe in that design space to understand, in this 50-dimensional design space or 10-dimensional design space, to understand where is maybe the best variant to be found. And okay, even though it's shown here with a little figure, this is what the computer systems do on your behalf. Okay, there are typically 2 phases that we distinguish. One is called the exploration phase, and the other one is called the exploitation phase. Exploration means you want to understand the design space a little better. Say we have a 10-dimensional design space. We don't know which parameters, settings would give us the best result. So what we could do is you go very systematically. Okay, like in this little beach setup here, very systematic way to control that beach. It is called an exhaustive search. And an exhaustive search is great in 2 dimensions or in 3 dimensions, but really, really not a very good idea in n dimensions. So if you go, for instance, to a 10-dimensional space, if you just go 2 variants in each direction, you already need 1,000 variants to look into. If you have a 20-dimensional space, it's already 1,000,000. So if you have 1,000,000 variants to look into, this is not very good. 2, say, hours of computational time for your simulation per variant times 2 million, you'll be graduated by then, hopefully. All right, so the idea is we go for a design of experiment. A design of experiment is a very smart way to do exploration. And this is the other beach, so to say. What happens if you go to a beach and you want to be on your own? Well, if you are the first person, you pick the nicest spot. You sit down there, put up your umbrella, lay down your towel, everything's fine. The next person would probably also want, unless there's a certain interest to get closer, would want to be at a place that is more or less the furthest away from you, okay? So you come to the beach at the second group, you would pick something that is really far away. The third party would do the same, the fourth party would do the same. So we always try to be as far away from the others as possible. And this is what a design of experiment does on your behalf, with a very nice mathematical formula. Typical methods are Latin hypercube and the SOBOL. And I'm showing here, for instance, for a 2-dimensional problem where the SOBOL algorithm puts variance, okay, in design space. Now we have to picture this in 10-dimensional design space to get an understanding. The idea is always fill up the design space as nicely as possible with as few variants as you can afford. Okay, so now you might have a good region identified in your design space where you feel, oh, well, it's already a little better than from what I started with. And then what you want to do is, we call that an exploitation, and there are hundreds of exploitation algorithms around. That would be a whole lecture series in its own. I just want to sort of say, mention a few so that you would that you might have seen it or heard it. Basically, what an exploitation phase does is it probes around again. You are at a certain position, and you basically just go a little step. And if this gives you an improvement, hey, why not sort of say carry on and go for another step? And if this is an improvement coming from over there, having 2 improvements, I might as well sort of go diagonally through the space and bring home even better results. And this is shown here. No time to really go into the details. But again, it's an algorithm that helps you to go through the design space very nicely. There are things also that you might have heard of or that you might see at some point: genetic algorithms, particle swarms, simulated annealing, all sorts of algorithms that are around. And the good news is there's no optimal optimization algorithm. You have to test them a little bit for your specific needs and for your specific design task. So don't worry, if you have one that you are happy with, stay with it. It's not that the next one's coming around and it's always better, particularly not maybe for your particular problem. Okay, so ingredient 1, optimization. We have at least to say covered that there are some algorithms around. Now we have to look into how do we actually create geometry so that we can vary it. Vary it with as few free variables to keep the design space small as possible. And as you can see here, there are different techniques. I'll explain a few in a second. But there's also not one single technique that would solve all the problems, because some are very flexible and others are more efficient. And again, you have to find a compromise for your particular purpose, which one to choose. Say if you have a traditional B-spline modeler, you can do whatever you want, okay? Very flexible. But each vertex that controls your geometry can, by definition, be moved in 3-dimensional space. So every single vertex gives you 3 variables. And if you have a 20 by 7 control polyhedron, 20 by 7 is 140 times 3, that's a lot. So you have a very large design space already. Hence, you have to move a little bit towards higher efficiency but less flexibility. And this is what we do with parametric modeling. And we distinguish 2 things: partially and fully parametric modeling. And I'll show you an example for partially parametric modeling. You have maybe your geometry, it's a bulb of a carrier, and you want to modify it. So the actual geometry is already defined, but now you want to modify it very nicely. Maybe you just want to check, okay, is maybe this bulb a little better for the purpose, maybe at the speed and the draft you're going, or is that one the better? Okay, and this is what we now call a partially parametric model. Namely, you have a dead geometry, say out of Rhino or out of your favorite CAD tool. You have spent several hours in setting the geometry up, and now you so to say spend a few hours or a few minutes, in fact, to set up your changes that you want to make, and not fiddle around with the underlying definition, because that will typically give you too many free variables. Okay. Another example of partially parametric modeling is freeform deformation. It comes from the movie industry. You basically have a volume, a B-spline volume, and the B-spline volume has a lattice of vertices, and you can embed your geometry into this lattice and now modify certain vertices in your control volume, okay, and again, you might then just put certain vertices together so that you would control the geometry with very few free variables. The example over here is from a Stuttgart-based southern part of Germany engine manufacturer. They have nice cars with a little, so to say, emblem that looks like a star. It's a catalytic converter. I'm not allowed to say which one it is. And as you can imagine, we changed the geometry with this freeform deformation, and to go into the catalytic converter, you want to have a very homogeneous flow field. So another example, not so much from naval architecture, but it nicely shows how to use those freeform deformations. Okay, or yet another one that is a topology-based morphing technique where you have the same topology, and if you have the same topology between, say, two extremes, the one over there, the bluish one, and the one over here, the green one, you can, of course, somehow just go in between. So if you have 0.5 of blue and green, you end up over here. If it's a bit more blue, you'll end up over here. If it's more green, you can end up over here. So it's a one-dimensional problem, even though you have a rather complicated design geometry. It's not super complicated, but the duct at least doesn't look like you can do it with just one free variable, or with just one parameter. And you can extend that into 3 dimensions, 4 or 5, whatever dimensions. If you have, say, 10 bases to choose from, then you have a 9-dimensional design space that you can work with. Okay, and yet another partially parametric modeling technique, which is extremely nice. It's called radial basis functions technique. Again, shown for an automotive example. You have your geometry as is, and you basically just build up a 3-dimensional vector field, whatever that is, to modify the geometry in that region that you identified. The darker greenish blue thing is where we want to make modifications. The red line or the red curve giving you the roof geometry, that gives you an idea of the initial geometry. The green one is what you want to modify to, and now we can more or less morph between the original and the new one. You can even extrapolate a little bit in both directions, and again, modify everything very nicely with very few free variables. Why would we want to go for very few free variables? Just recap. If we have a high-dimensional design space, as I've shown in this little example of the exhaustive search, the more variance you have to understand and have to build to get an understanding of the design space. The typical rule of thumb that's important to remember is the square of the number of free variables you have to investigate. If you have 10 things to change, to choose from, your free variables, you have to look into 100 designs to understand the design space, more or less properly, unless it's super wiggly. Okay, if it's a very complicated design space, that would not be enough. But at least in aero and hydrodynamics, it's not often the case. It's not like that a design space is really wild. Okay, fully parametric modeling. You can use fully parametric modeling very nicely to make really complicated shapes with very few free variables. And I'll show you along that line of the fast monohull that we have seen at the start, we basically just lay out curves in one direction, typically a longitudinal direction for a hull, and from which we can produce what is called a metasurface. A metasurface is a specific type of surface that readily uses all the input from a pattern and from those longitudinal curves to build the surfaces. Okay, now we have a fully parametric model. We can make global changes, or we can make local changes. So for instance, if you are not quite sure about our hollowness in the hull, or if, say, a bit more dead rise might be better, it's all controlled with just a parameter. You don't have to fiddle around with the vertices because they come more or less for free by means of the modeling technique. No worries. It's a complicated enough thing. It's just for you to keep in mind that you can do it, and if you want to do it, we have to take a closer look at another point. Okay. And of course then, if you want to go into the simulations, you have to produce what we would call a watertight geometry, because that is what a typical, say, CFD code would expect from you, okay? No gaps, no overlaps, little triangles that are nicely distributed in your geometry, and everything is connected. So watertight, there would not be any, so to say, gaps. And from that then you can generate your grid, your mesh, and start your simulations. Okay, this is the mathematical explanation to how that works with the metasurface. I'll skip that for the sake of time. And just so to say, in addition, of course there are always things that you need to model that are important both for the simulations and for your later product, but that you might not readily want to capture in your initial parametric model. So for instance, those fillets here that you can see, is the green part of a propeller blade put into the shaft. That is controlled by a different technique, and you don't want to capture everything in a single model, but you want to put things together in a hybrid so as to be able to control them nicely. And if you talk in hybrids, you can of course also combine the fully parametric and the partially parametric modeling techniques. So it's not that you have to decide at the start, oh, I'll go for this one and then I'm stuck, or go for the other one, but that's a lot of work. But you can combine it as need be. Okay, constraints. I already said, okay, a typical constraint is that, for instance, you might have to have a certain displacement for your hull, or you want to have a certain center of buoyancy, or the center of buoyancy has to be between this and that. That would be inequality constraint. If it's fixed, it's an equality constraint. If you say, okay, it's 1,000 tons and nothing more and nothing less, then okay, it's an equality constraint. Often things are inequality constraints, luckily, and you have to sort of say, look into them. On the left, you see, for instance, inequality constraints for a duct. It's a cooling duct for a brake system of a car component. Okay, so if you look very closely, you can see the grid for the cooling system, and the part goes into a lot of other systems and has to say live with the space that's available. So a constraint, an inequality constraint here, is wherever we are getting close to the other components, check the distance, and if the distance is below a certain threshold, then you're gone. You cannot do this. It's called an infeasible design. So you might just say 1 inch is minimum. So wherever I put something into this space for my duct, I have to make sure it's at least 1 inch from all the other components away. Or it's also from automotive industry. It's a piston ball. Typical example where you need, if you have a diesel engine, for instance, and some of the larger engines in naval architecture are, of course, diesel engines. If you want to keep, if you want to do an optimization, you have to keep displacement here. It's crucial. Otherwise, you would compare apples and bananas. So it's an equality constraint where every single geometry has to comply with the constraint of this is your compression ratio, and that has to be constant. And what can you do now? This is actually an advantage if you have an equality constraint, because you can take out one of your free variables and, so to say, sacrifice it to capture that equality constraint. So from a 10-dimensional problem, you might actually go down to a 9-dimensional problem, and you use the 10th free variable to check that the compression ratio is actually really computed. You can do this with an inner nested optimization. So just to give you an idea that, of course, we have to capture all those. Well, this is one of the few advertisements, so to say, as Professor Honors already said. I'm with a company, Friendship Systems. We have this one product, Cases, that you use for simulation-driven design. It was, for instance, used by Ineos Britannia, who was successful in the Louis Vuitton Cup, not so successful then in the second round of the America's Cup. But as you can see here, within the cup constraints for the last America's Cup, there are literally hundreds of constraints. It's a book of constraints, more or less, where everything is written down, inequality constraints, inequality and equality constraints, a lot of things. Just to give you an idea, for instance, that mechanism to bring up the sword system and the foils always, of course, has to be in there, in the hull, and you have to more or less wrap around the hull so that it would fit at a certain position with certain distances, etc., etc. So you can imagine this is something when you want to run thousands of variants, you don't want to do this manually. Maybe for 10, okay, but for 20 it already gets boring, but for 200 it really feels bad, and for 2000, no way. All right, just another view on those Ineos hulls. Interestingly, Ineos Britannia decided, on the basis of simulation design, to go towards a completely different type of hull. Most hulls, including the one from the US, were as small as possible, while Ineos Britannia in the end came up with the largest hull. And their thinking and design thinking of that design was coming from the simulation-driven design effort, and it would actually give you more control and more reduction of downwash and of a certain advantage at lighter winds. Okay, a few more examples from various industries. I'll of course focus on the maritime industry. You might find a few companies that you are familiar with. Yamaha, for instance, American Bureau of Shipping. And as you can see, it's really a global thing. I would guess that very few larger vessels are now built without running simulation-driven design campaigns. It's just that you can squeeze out so much more than doing things manually, that no one now, with energy being extremely costly, also with the environmental impact, or when you look at battery-driven boats and ships, you can't afford it to do it manually all the time anymore. Okay, so let's take a look at an example that our customer Foyt allowed me to show. It's a thruster. It's actually a pretty big thing. I'll show you in a second in comparison to the person that actually did the design. So we have a parametric model, fully parametric model in that sense. It's up there in the upper left here. Things that you would typically have for a thruster or propeller, like pitch, rakes, Q, thickness distribution over the radius. So you start changing this, and that of course will impact your hydrodynamics. For the sake of showing this or being allowed to show this, I'm not showing the changes of the duct itself. We're just able to show the changes in the blades. And what you would then have, after lots and lots of changes, you would have a typical picture like this. Okay? So this is now a multi-objective problem for that thruster. Thrust is one objective. Cavitation volume is another objective. Cavitation volume you want to be as low as possible, okay? So we're going towards the lower left part. Thrust is what you actually like to have, so you want to go as high as possible. And what you can see here now is what I illustrated at the very start of the presentation is a Pareto frontier, okay? So there are designs starting from the baseline that was a manually produced baseline. You can now decide, okay, I have another design over here that's actually performing extremely nicely with regard to thrust. Same thrust, but cavitation volume has shrunk. Great. So we have less cavitation for the same thing that we produce, thrust. Or you say, our cavitation volume is all right, but I need more thrust because I might have to control, it's a dynamic positioning system, I might have to control a larger floating structure or something, so I need more thrust, but cavitation volume is fine, so then maybe this design over here is going to be the better one. Or anything in between, a compromise where you say, a little less cavitation volume would be great, but more thrust would be even better, so maybe I'll, I don't know, pick one of those, okay? And this is what simulation-driven design now allows you to do. Imagine you had only maybe 5 designs. Okay, then you can take this one, or that one, or that one. And now, as we can see here, from the design numbering in the lower right part, they actually produce several thousand designs, and from those you can pick. But what is also very obvious, you produce a lot of designs that are actually worse than your baseline. So everything over here and everything below here is not performing as well as from what you started with, okay? Producing something that's not so good is actually rather easy. All right, and this is that thruster in the end, and that person, I mean, they are not really small, they are my size more or less. You can imagine it's a massive thing, okay? Good, another example, a power system for ships. It's by MTU, a company in the southern part of Germany. They do large, fast-running diesels. And for these type of engines, you would typically need a turbocharger. Then you would think, okay, turbocharger, this is really a small element in that large engine. But they computed that a 1% rise in turbocharger efficiency increases engine performance by about 0.1%. And that makes up several $10,000s of dollars or euros per year if you run that engine. So it's smart to invest a little bit of time and effort to really save that stuff, because that engine is probably running for 25 years. So you can really save a lot of money in the end for your customer. Okay, without going into the details, let's take a look at this turbocharger. Again, this is a fully parametric model. It's the turbine of the charger. Maybe just to go back, the idea is you take some of the hot exhaust, you drive the turbine drives the compressor, and the better the turbine, the better the turbocharger, the better the compressor, the better the turbocharger, basically. So the idea was, can we improve, MTU, improve that turbocharger further? And what you see here now is a fully parametric model, and with things that are extremely difficult to model in a standard CAD tool. For instance, those cutaways, because they are not needed for, in this term, for the hot air or exhaust, but actually you can take some material away, everything gets lighter, and you can actually improve not only the design speed performance, but actually also the running up to design speed. In a turbocharger, you have these complicated diagrams. Don't worry about them. Basically, what I'm showing here is efficiency versus pressure. The green one was the one they started out from. The blue lines belong to the final turbocharger, which I cannot show, but it's among that family of turbochargers. So you see that we have an improvement, indeed, of about 1%, as they hoped, and actually even, so to say, covered the operating range a little better. And a direct comparison then shows, for the same diameter, because otherwise you would compare apples and bananas, you have a little less mass, 70%. That per se is nice, because you have less material that you spend, but it's not changing the situation too dramatically. You have less moment of inertia, 24%, so the turbocharger is running up much faster. And we actually, so to say, reduce the centroid of the turbocharger impeller, meaning that everything around it, the periphery, can actually also get smaller, and the number of plates reduced, and all for more energy efficiency. So, and it's a multi-objective problem, as you can imagine. Another example, fast monohull. Now we are going again a bit more maybe into your interests, I would hope. It's a fast monohull, think of a Coast Guard vessel. This actually is a pilot boat in this particular situation, 36 feet long, 9.5 tons of displacement, should go at a speed of 27.5 knots. For the hydrodynamicists, it means that we are a bit above the critical point of being planing. When you take the volume fruit number, if you are above 3, we typically say it's planing, or if you have the fruit number based on beam, it's a little bit above 2, 2.4, and this is also an indication of planing. There are a few other indications, like the center of gravity goes up, we have a cleared transom. Okay, it's at the lower region, but even more so, you have to optimize. Okay, let's have that quick look now. Different geometries. We have a bare hull. We have a tunnel because the shipyard that wanted to build that thing wanted to have a traditional drivetrain, shaft line, bracket, propeller, rudder, and so as not to increase the draft dramatically, they said, okay, we'll go for a tunnel. Okay. And then you start doing the simulations. For this particular simulation, we use star CCM+, and because the objective was supposed to be thrust, because thrust is more important than resistance in terms of optimizations. Let me just rerun this so that you can see it again. So it's a overlapping grid technology with many cells, above 3 million cells that were spent. The overlapping grid helps you that you would have, with this reasonable number of cells, a very fine resolution of your free surface, of your pressure field around the hull in any case, and around the appendages. Okay, so very many cells very close, and then gradually go into fewer cells outside. Why thrust as an objective? If you take resistance and omit the effect of the propeller, you get a different pressure field in the transom region, and that will change your running attitude, and the running attitude will change your resistance and your trim and everything. So you will not optimize for the actual situation that you hopefully encounter then in real life. So for this particular design, it was important to look at thrust, because then the propeller effect would be captured. Now, it was not a turning propeller, so to say. That would have been way more cells that we would have needed, but it's actually an actuator disc taken in the data from a tank test of the propeller, so we would have thrust and torque according to the tank data, and could adjust the propeller such that resistance and thrust were in balance. And the objective now is get the hull that gives us the lowest thrust. Okay, that's loud. Sorry for that. Turn it off. But now everyone is awake again. It's a typical tone tank test done at TU Berlin to understand how close do we actually get with our simulations towards a not super easy simulation situation, okay? Thrust for a fast monohull. And I'll do this very quickly. Resistance, for instance, was extremely well captured. So for an initial geometry, you see here in the dashed lines the experimental data, and in the solid line the results from the CFD analysis done with star CCM+. And nicely, okay, you have to believe me, the simulations were done before the tone tank test started. So it's not that we had the tone tank data and said, okay, let's fiddle around with all the setups for the CFD until it really matches nicely. But we ran the whole thing and then realized, hey, wow, this is really good. Typically, if you are maybe plus minus 5% away, everything is really okay and nice. In this particular situation, and we had guys from Siemens helping us to set up the simulations nicely, it's within this plus minus 1% resistance accuracy that you would see in a typical tone tank test. And even then, if you start to introduce small changes, we introduced a change over here in the tunnel region, the model that was built actually allowed to just take out the tunnel and put in another tunnel. And I mean, it's really, really small changes. And you already see that those changes change the hydrodynamics, and they are nicely captured with the CFD code, okay? So it tells you you can believe the CFD to help you find a better design, okay? And then you run the design of experiment, as I explained, and you would typically get pictures like this. Lots and lots of, so to say, data points that you now have to try to understand. Let's just take a closer look at this one row here. It gives you thrust as the ordinate versus different parameters. And as you can see from the coloring and from the correlation lines, if they are very horizontal and the coloring is green, it's not such an important parameter. But if it's, so to say, yellow or orange or red or blue, there is a lot of, so to say, to be changed when you change a certain parameter. For instance, those two over here that are highlighted, it's two parameters that control the tunnel geometry. They really make an impact. If you got them wrong, then you pay, so to say, a penalty in resistance. If you get them right, you, so to say, actually improve your hull geometry. Typical picture from a design of experiment, as I hope to have explained, is like this. Lots of designs in the blue region that are actually not performing quite as well as our baseline, but also, as you can see below the blue rectangle, everything that is, so to say, a blue dot is performing better than the baseline. So we have an improvement already just from a design of experiment here of around 5%. And then you can maybe pick, because for instance that was one that the shipyard really liked, said, okay, can we maybe make further improvements from there? So from the exploitation phase, we went into the exploration phase. Okay, sorry, from the exploration phase, we went into the exploitation phase, trying to cover the design space and then bringing it back and making it even better. Okay, let's take a look at flow fields and at the designs. That was the design we started out from. That was the actual baseline from which the optimization started. So there were some manual improvements. I'm not saying that you would not be able to do manual improvements up front, okay? Don't start with a box and hope to get a nice hull form. You want to start with something that's already pretty decent. Okay, and this is what we call the third optimized design. I just go back and forth a little bit so that you would see changes. Maybe take a look at the rocker that's over here. There's a rocker introduced, and also maybe take a look at the dead rise when I changed the geometry from the third from the new baseline to the third optimized design. Okay, so there are changes in the geometry, there are changes in the pressure field, and also changes in the wave field, as you can see here, and this actually gives you then the reason why we have an improvement. Let's take a look. Thrust was our objective, okay? So at model scale, running the experiments, we have an improvement a bit above 14%. So that's quite considerable. And starting not from a really crappy design, so it was a reasonably good design to start from, and we still managed to get 14 point something from the experiment and around 11% from the CFD. That's also often to be found, that you would have maybe a little overshoot, you have a little bit more that you gain in the experiment, or a little less that you gain, but still you gain something. If you have an improvement, as promised here, 11%, and then you get away with 14 point something percent, no one is asking questions anyway. If you promise 11 point something percent of improvement, and then you only have 8, then of course people start asking questions. But still, 8% might be better than nothing. Okay. The thing was then built and actually also model tested. Not sure if I switch on the, okay, it was allowed to. And that would then allow us to do a comparison between the model tests and the CFD runs and the actual results from a very extended full-scale sea trials. And the sea trials are shown here in these blue dots. And the prediction from the model tests are shown in red dot and so to say little symbols. And that looks pretty cool. I mean, it's very close. I'm not showing the one thing that was not quite so close. We actually also measured thrust, but the thrust measuring device, which is an extremely complicated thing, was not performing quite to what we hoped. So I'm skipping that. Okay, I have just a few minutes left, and I won't bother you with yet another big thing. I just wanted to mention that if now we are not looking into a single objective problem, like a multi-objective problem that we had for the thruster, for instance, or for the turbocharger, does it make sense to have all the simulation codes combined, and everyone needs a specialist to run it, and it's complicated stuff. You need special hardware, you need your software licenses, etc., etc. So it might get complicated if you have a lot of things to look into. But there are ways to capture that too. We call them synthesis models. And the essence of a synthesis model, I'll show you a few synthesis models just so that you see they all look different and all complicated. But what I wanted to bring home in the last 2 or 3 minutes is, if you have many things to look into, why not produce your own numerical series up front? So you might just say, okay, I'll produce a hull form and I'll run 500 CG runs up front so that I would have an idea, for instance, on the resistance, on the thrust for different geometries. And you can do that not only for your hull form and for resistance or for thrust on propulsion. You can do this for sea keeping. You can do that, as shown here up to the left, for intact and damaged stability. So for all sorts of things. And you just do this up front, maybe with your specialist, and then you have all the data. And if you have the data, you can then go the next step from simulation-driven to actually data-driven engineering. Okay, and without, so to say, going into the details, basically what you do is just use artificial intelligence. It was something that, like the drop back, I had to say. Otherwise, you would probably say, hey, he never used the word artificial intelligence. Why not? It's actually built in here. Namely, when you have a lot of data, you build what is called a surrogate model. Surrogate modeling is part of machine learning, and machine learning is part of artificial intelligence. So there it is. But don't worry, it's not that complicated. It's what you have done in school and definitely also in undergrad studies. You have a lot of data and you more or less say, okay, it's maybe linear or quadratic or whatever relationship between the data that I'm interested in. Okay, and the methods just get more sophisticated if you have an n-dimensional problem. And then you would use something like an artificial neural network, for instance. If you have a 20-dimensional problem, well then maybe a polynomial regression wouldn't work that nicely, so you use that artificial intelligence. And when you have that data, and you capture the data, then you don't have to run a simulation that's costly, but you just use the data to look up the performance, and then you can go through a very complicated design and produce Pareto frontiers and results for very complicated design problems. More on this another time, maybe online. All right, so that brings me to the end of my presentation. Just remember, Friendship Systems, that's the company. It's another advertisement. We are around 30 people, mainly naval architects, mathematicians, software developers. We've worked on this for many, many years, so bear with me that within, say, 50 minutes you could not get everything that I said. Hopefully you are interested now and you'll be, so to say, looking into simulation-driven design a little further. Thanks a lot.